Okay. Almost there. Okay, yep. You good? Alright. So fine. Alright, so today we're going to talk about Chapter 9. Chapter 9 is about databases. So for you two, it's review. For you, it's
I've got audio too. So
information overload, basically. It's like half the database class in today, and the other half was when we talked about ER modeling. So Thursday we'll talk about Chapter 10. I already posted, I will post slides. They're done, I just haven't posted them for Chapter 10. And then we'll have an exam next Tuesday. I'll put a study guide up too, since I know. So this will be the only exam we have. So, and this will be the last week where we're slogging through the book, and then we'll just be doing project stuff basically. So I haven't made it through all the assignments yet. I will by the end of the weekend, work 1 and 2, so that we'll know for the last 10 weeks where we're going forward with projects, and then we'll start doing a rapid cycle through the software development life cycle. So we'll do requirements, design, implementation, as much as we can, and then we don't really wrap the project up. That's kind of the end of that's what Chapter 10 will talk about, is implementation, and then what do you do at the end of a project. So we'll kind of do miniature versions of all of that stuff, and then 1 minute. That'll take us to the end. So the test, and I'll send an email for everyone else. I'll just make it available on Moodle all day, and it'll be, open, whatever. More of just interpretation of some of these things. Like obviously, I'm not going to ask you facts because just
that's not me. I can Google search.
Since we have online and in person, it's got to be online, and if it's online, it's open book as far as I'm concerned, because I always say everyone will do it anyway if I say it's not. So yeah. Or maybe a couple people won't because they're super honest, and then they just get screwed because everybody else does. So, right? I mean, that's kind of how it ends up working. So,
It's past everyone now.
so it'll be available all day, but I think we'll still slice out class time to do it in here for those that want it. We'll talk some. It's not going to be an hour and 20-minute exam, but well, I will probably cap it that you have like an hour, but of course we can work within that. But so that we can keep going on. There will be one last homework assignment from the book that will come out within the next day or so, kind of leading us towards the test. So it'll be good review for the exam anyway. I mean, we didn't do a lot of homework from the book in the past. They've done a lot more, but we also went quicker. So I just didn't think that was worth answering tons and tons of questions, but I'll pick out some from the latter part of the book. And then as we move forward through the project, there'll be deliverables that are basically homework. Like do your requirements. That'll be kind of a homework, the piece of the project, and then the end culmination, that deliverable is like the project grade. I think that's like, and then you present it, and that's 25% of your grade, whatever I have on the syllabus. And exactly how I broke it down, but yeah, so 30% for that kind of end, but this 50% will be the 3 homeworks we've had plus kind of the pieces you get. All right, so the databases. Chapter 8, just remembering what we talked about. We talked about just how to design. That was really what it is. Some guidelines, a lot of lists, but good stuff to kind of remind ourselves of what makes a form, a report, a dialogue, what makes those consistent, usable. We had some formatting stuff, how we should provide feedback, that kind of thing. Chapter 9 is basically just called designing databases. So it's the part of database class where we took our ER model, we made a database out of it. So, I mean, I question whether we should even go through this because we just came off database, but I think it's a good review. I mean, it's always good to rehash something again because then you start to really, it sinks in. Plus, some of the way the book talks about it is a little different, and I kind of like that. I just think, you know, our last book had a certain way of going about it, and you're going to encounter all sorts of different ways to discuss databases. So I stuck with what this book does, I didn't just switch it up to be like our last book because I think it's good to have a different perspective on these. And then, of course, for the 3 people that didn't take databases, this at least provides some guideline. Obviously, you're not going to learn half a semester today, but so hopefully these are very familiar to you guys. But we'll talk about relation, primary keys, functional dependencies, foreign keys, referential integrity, fields, data types, null values, denormalization, file organization. This didn't really come up in our database text, but this is taking a look at beyond. We just always say, well, you use the database management system, and it doesn't. We'll talk. This book talks a little bit about more how that actually gets structured. So we'll talk about that a teeny bit. Indexing, which we did talk about, secondary keys. So I think all of this is just straight from databases, other than that file organization thing. It's kind of new and kind of a little bit different. So just the role of designing database, how does it fit in with some of these other pieces? We've had our data model, what's that called? What is the acronym? Data flow diagram, DFD. Too many things to remember. Our data flow diagram, and then our conceptual model, our ER diagram. How do those feed into the actual design of the database? Transforming an ER diagram into a logical database design, which we of course did. This book does it a little differently, which is actually closer to the way I was taught versus how our last textbook. Our last textbook really just said, yeah, it kind of just said do it, and if every, what was the rule we had that it was in DNF form, every candidate key is, how do they define that? I'm like totally blanking. Yeah. How, whatever, it basically just said do that. This book goes through more, it's going to drive me nuts. We talked about that like, what, 100 times. This book goes through a little bit more systematic procedure for doing that, which is how I was taught. And I mean, we won't go super deep into it, but we will. It's good to see this other way. So, I'm going to figure out where the heck that is. Someone said it last week, the exact statement, and now I'm blanking. Every functional dependency is a candidate key. Isn't that what it was? So we'll talk a little bit about normalization, how to take something that's normalized and consolidate. We'll talk about denormalization too. Storage formats for database tables. This is kind of the new part. Efficient tables, we kind of talked about that, but that involves indexing, and then this file organization. So, database design. So logical design in contrast to the conceptual data model. Conceptual is ER diagram. Technically, that doesn't have to be related to databases. It's just a model for the relationship of data. It almost always then goes into a database because it's just, they're kind of paired together. But the idea is one is conceptual, one is more solidified. So 4 steps: develop a logical data model for each known user interface using normalization principles. So the idea is every piece of a user interface involves data. Where is it coming from or where is it going? So you need to have a data model that goes with each of those. And like if I pulled up orbital shift, you go to the employee page to edit employee information. Well, that would map to an employee table and a certain table to go with it. Combine normalized data requirements from all user interfaces into one consolidated logical database model. So they're starting by looking at each interface and saying, well, we have these requirements for data. We have all these pieces. How do we fit those together? What parts overlap? What parts are different? How does that tie together? So translate the ER data model for the application into normalized data requirements. And then step 4, compare the consolidated logical database design with the translated ER model. So what they're saying is you have your conceptual ER model. You have this one made by looking at your user interface and your planning, and you kind of develop a logical model for both, and then you merge them together. That's, I think if you're good with databases, you really need to do that 2-step consolidated database design with the ER model. I think you could just do the ER model. The idea, though, is, the ER model should be driven by your data flow diagrams and those pieces, but they're layering this user interface in because you might have missed something. And then you say, oh, wait a second, on this screen, the user needs to log in with the username. We forgot to store their username in the user table, or that kind of thing. So sometimes when looking at it from the user interface perspective, you'll find things you missed. So physical design is basically the results of the logical design. So it's going one layer down. This is kind of going a step below. Like in databases, we just assume we're using a DBMS. This is involving an extra decision there. So choosing the storage format, we didn't really deal with that, right? That was just sort of there. Grouping attributes from the logical model into physical records. How are they actually stored? Arranging related records in secondary memory. So, again, we just assume we're using a big DBMS and it's doing it. There's a little discussion in here about, I hope you're not using magnetic tapes anymore. When I ran a backup server for the whole business school on the campus, we were feeding tapes in 5 years ago. So, is there any tapes around here anymore? Because what were those tapes? Gigabyte tapes, or I think they got up to gigabyte was the biggest tapes. And we had a HP server 6-7 feet tall. Had the server, had all the tape management, and it rotated them so it didn't write in the same spots on all of them, and it kept track of the age. And when they got too old, I'd have to feed a new one into it. It was so weird that was part of my job because it had nothing to do with anything else I did, but because my office was the server room and it was there, I think that's why that became part of my job. But no one knew how to get anything off the server or had ever tried it, ever, and it had been running for a long time. And it was discussed, maybe we should do a simulated restoration at some point just to see, do we even know how to use this thing? It never happened. So it almost happened once. Some professor deleted something and really needed it back, and they wanted me to try to see if I could recover it off the tape backups. They ended up using shadow copy and getting it that way, which I was glad about because I didn't have to do it. But yeah, I think it wouldn't have been that big.
I used to have a deck on my house.
Yeah. Selecting media and structures for storing data. So I mean, this is like physical. We're dealing with the actual computer hardware. You checked it and I started this, right?
Yeah.
You didn't run. Yeah, someone's viewing. Is that you or is
No, I
that
got mine.
I wish I could see who was viewing. So maybe how does this thing work? All right, Mr. Ron Burgundy. All right, I guess Ron Burgundy is our viewer. It's really Aaron though. All right. So now we're getting into that giant list of definitions that hopefully you should remember, otherwise you didn't learn. So primary key, basically that's just an attribute whose value is unique across all occurrences of a relation. Now, of course, we know that there's candidate keys, right? There could be more than one thing that's unique. The primary key is just the one we picked out of the candidate keys. They don't really go as much into that whole idea in this text. As I've said, this text is kind of aimed at more business people than more tech people. It's, I don't know, it's kind of in the middle, so they don't delve. Some things they go a little more detailed about the database, a lot of them less. Of course, it's one chapter, not a whole book, so. All right, so deliverables and outcomes, and why the book kind of goes in the order it does, but primary key, and then we're going to talk about deliverables. So logical database design must account for every data element, system input, or output. And that can seem kind of overwhelming, right? Like you think about every website you use and every piece of data that goes in and out. I mean, it's a lot. The primary end result of this process is a set of normalized relations. And then basically you're just converting that into files. Now, again, we're using a database management system. We're going to just take those relations and put them in there. And yeah, there's a file there, but we're not dealing with this. I don't really know many cases you would. Depending if you're creating a system, you might use a flat file structure like I've talked about, or an XML or something slightly different than a database. Then you're dealing with the files directly. But if you're dealing with database design, you're probably using a management system. And that's going to kind of do that for you. So, relational database model. So the idea is that we have related tables. Tables and relations are the same. Okay, remember, we have all these parallel terms. We have entities, tables, relations. We have tuples, rows. We have fields and attributes. It's like the same words for different things. So a relation, which is a table which comes from an entity on our entity relation model, is a named two-dimensional table of data. So it has a set of columns and some arbitrary number of rows. The columns are defined and fixed. There might be no rows because it doesn't have anything in it. There might be a million rows, just however many pieces of data. Properties are basically the entries in cells. That's what they call in here. Entries and columns are from the same set of values. So if you have a column that's first name, that whole column contains first names. So you're just getting at like basic table structure. Each row is unique. So a property of a relation, I guess is how they're saying this, is each row, you can't have duplicate rows or it's not a valid relation. That's where the key comes into place. The sequence of columns can be interchanged without changing the meaning or the use of the relation. So there's no, it could be last name, first name, it can be completely random. There's no, this is first and that means something. When you get that data back from the database, as we saw in the PHP code, you just reference the name of the column. It doesn't matter in the database what order it was in. The only advantage for it being in order is the people that have to work with the database. It just looks nicer. If you want to pull up and run queries on those, by default, it goes left to right as they're ordered. So it makes sense to put first name, last name, rather than first name, 20 other things, and then last name. But of course, it's all arbitrary. I can write my select query to return those in any order I want. It's just how I list them. So there's really no meaning to it. Rows can be interchanged or stored in any sequence. So there's no sequence of rows. Like this is row 1, this is row 2, 3. Even when we use a key, like an index or an auto-incrementing key, you know, they're in order, it seems like, but as they're stored in the file, it does not matter. And we talked about it before, orbital shift. We hit a certain point where things started coming not in order, even though they were in order in the database, and it caused me all sorts of problems. The order doesn't matter. You use order by in your query, and you just force the order, basically. If you have a relation that doesn't meet one of these, it's not a valid relation. If you have created something where the order of rows or columns does matter, that's just not valid. It won't work, basically. You need to reconsider your design. So well-structured relation. So this is starting to get into normalization. Has a minimum amount of redundancy and allows users to insert, modify, and delete the rows without errors or inconsistencies. So if you can meet those other properties, it'll be well-structured. Well, you'll be part of the way to be well-structured. So it's also normalized. You can meet those and have something that has a ton of redundancy, right? So there's a couple layers here, but here's just a simple example of employee, name, department, salary. Now, we'll keep going through breaking this down, but right from the get-go, they say this is well-structured, and I'd say there's two things that are awful about this relation. Yeah, marketing is on there twice. What else? What's the other thing that jumps out that's not a good design? Yeah, the names are in one column. You should always split them into first and last, because otherwise, I can't order this by last name. It's impossible. Unless I wrote code to go through and split based on the space, and it's just a huge pain. First name, last name. Department, we have redundancy. Now they're saying minimal redundancy is okay. What if we had 1 million rows? You're going to have a lot of marketing in there. And then what if I decide marketing, I'm renaming that department? I'd have to edit 100,000 rows. And this is where we get into the, it's better to have the departments in a separate table and then linked into this table. Oh yeah, they're not in order by ID. And that's just basically, as just strictly the relation, the order doesn't matter. We could organize it better when we pull the data from the relation. Yeah, you could sort it. Yeah, exactly. Yep. So, yeah, I mean, it's well formed or well structured, but it could be better. So, normalization. So this is the process of converting complex data structures into simple, stable data structures. This is like quite a different definition than the definition that came up in our database book, but it makes sense in some ways, because in some ways it takes a structure and breaks it into all these other pieces. It almost seems more complex, but the key is this stable data structures. This isn't that stable because if we want to rename marketing, it's hard to accurately do that and ensure that it happens everywhere. A better, more normalized version of that would be more stable. Also, normalization will eliminate redundancy, which we already said. So, here's an example of an even worse employee table that has a lot of redundancy. So, the idea here is that this is courses. Margaret Simpson is taking these 2 courses, or no, she took them. This is when they were completed. All this stuff's duplicated. Her name, her department, her salary. The only thing that's unique here is this. So as we know, we'll see in these later slides, this should be broke out to its own table, linked in with the employee ID. So this could be normalized. And there's one of the easiest ways to look at a table and say, does this need normalized, is if there's redundant data. That's kind of at the most basic level, the simplest way to say whether something is normalized. Now again, as we talked about in databases, that requires there's data in there, right? So if you're making something from scratch and you don't have it filled in, you might not notice it. But for existing things. Right. Yeah, there's almost like 3 layers of redundancy here. You should be able to just save the course, and when it was completed, you don't need to save that date again. If Austin was here, he could talk about the database stuff he's been working on and some of these exact problems of redundancy and how they're trying to merge those things together. So now we're going to talk a little bit about these normal forms, which, the last semester we kind of just skipped straight to the voice COD normal form, the BCNF, and said every functional dependency is the candidate key. I think that's what it is. I don't know. I wish I could remember the exact wording of that. But this book breaks it through, which is how I was taught. You start, you check, is it in second normal form? You check if it's in first normal form. You check if it's in voice COD normal form. You kind of step through a procedure. So for something to be in second normal form, each non-primary key attribute is identified by the whole key. So this is a different kind of definition that we had. The idea is that any candidate key can be linked to the primary key, can be determined by the primary key. So for example, if you have social security number and student ID number, and you say social security is your primary key, you could use that to determine the student ID number. There's a one-to-one mapping there. But if you had a different version of that example, second normal form, most things, you'd have to try almost kind of hard to make something that's not second normal form. It's almost like where you have 2 separate candidate keys that just aren't really related to each other, and they might be unique amongst themselves, but it's not in the same one-to-one pairing. I'm doing a horrible job of explaining this, but so third normal form, non-primary key attributes do not depend on each other. So that's that transitive dependency we had. This depends on this, and this depends on this. You don't want to have transitive dependencies. And of course, our ultimate definition in databases encompass both of these. by nature. Amber's going to find it, and then we'll be happy. I can't believe I can't remember that. I know what it is, like practically, but the statement. So the result of normalization is that every non-primary key attribute depends upon the whole primary key. That's basically a restatement of what you're looking for. They're just saying it in a different way. Pause there for a second. I want to compare and contrast these definitions. So I was trying to just do it. Every determinant must be a candidate key. So we were saying it slightly off. Every determinant must be a candidate key, and the determinant is something that something else is functionally dependent on, right? So every determinant has to be a candidate key. So here they're saying every non-primary key attribute depends on the whole primary key. So it's looking at that same idea from reverse. Our other definition is saying that the determinant has to be a candidate key. This is saying if it's not, it has to be dependent on the key. So it's the same idea, just in reverse. So functional dependency, it's always great to use a word here before you define it, but we know what they are. So functional dependencies, so this is the idea, it's a relationship between two attributes. So B is functionally dependent on A if for every valid value of A, that value of A uniquely determines the value of B. So it's one of these wordy things. But basically, if I can say I know A and I 100% for sure know B, that's a functional dependency. So that's like the social security number. If I know the social security number, I 100% know the student ID number. I know the name. You know a lot of things if you have the social security. Now, other things, phone number, if it was a key, can you say 100% you know the name? Not necessarily, depending on your structure. So I touched a lot on this in databases. Instances or some sample data do not prove the existence of a functional dependency. Even if you have 1,000,000 rows and you say for every row I have in here, this attribute can determine this, doesn't necessarily mean that that's right. There might be some case. Look at the reverse. Say student ID number can determine social security number. And I take everyone in this class and I put our social security number and I put our student ID number and I say social security number is functionally dependent on student ID. We'd say true, right? Because for all of us, there's a one-to-one mapping. But if you had a foreign student, they don't have a social security number. So their student ID number doesn't determine their social security number. If we just looked at the four of us, we'd say, oh yeah, that's a functional dependency. That's sample data. That's not every possible data that's out there. So you got to be a little careful with a lot of these decisions and don't base it on the data, base it on a higher level of thinking. And this knowledge of the problem domain is the best way to identify these. This is where it's hard. And this is where, like some of your projects, the databases, like Damon did mushrooms. I know nothing about mushrooms. So I had to really think about his functional dependencies. Like, is that right? Is this really functionally determine this? And ultimately just trust that he knows a lot more about it than I do. He even came up with some of the video game stuff where the guys that did video game things I questioned, is that really a functional dependency? They, maybe do a little more than I did about some of these things. So that whole domain knowledge. So now we're going to go back to these normalization things, and it's going to be broken down a little bit more. So there's some things where you can really easily say something is in second normal form, that it can meet this previous definition that each non-primary key attribute is identified by the whole key. If the primary key consists of one attribute, you're already good. It's only ever going to be in question is if you have a two-part primary key. No non-primary key attributes exist in the relation. So this is where, are there other candidate keys in that relation? If there's not, it's already second normal. Because where you get into trouble is that you have a second candidate key. It's not part of the primary key. It's kind of where you can cross this. Every non-primary key attribute is functionally dependent on the full set of primary key attributes. So that gets you to the definition that we had in the previous slide there. But the easiest check is to start with these, right? These are much easier to actually decide than this. This requires that you know all of the functional dependencies. These are a little, assuming it's well designed. Someone might have made a primary key and been wrong, you know, but if you know it's good, then that works. So to convert something to second normal form, and this is, our book did not, last semester I did not think went into a real great process of going through, though almost everybody designed something that didn't need normalization. Because I felt like by the time we designed, we kind of knew what we were doing enough that you weren't starting with garbage, so it was sort of normalized from the beginning. And I talked about that last semester. If you sit down and design a database and you have a bunch of stuff not in second normal form, it was probably designed by somebody that didn't know anything about databases. This is more of a thing you're going to do if you're working on an existing project. But anyway, so to get something in second normal form, you decompose the relation into new relation using the attributes called determinants that determine other attributes. So if there is a determinant that's not a candidate key, I mean, we're back to our definition. You break those out into their own new table, their own new relation. And then that determinant becomes the primary key of that new relation. So this is really well tying together our definition from last semester with the determinant. So third normal form. So for something to be third, it has to be second. That's just, these build on each other. To hit third, there has to be no functional dependencies between two or more non-primary key attributes. So that's the whole transitive. You have to have no transitive dependencies. If you do have a transitive dependency, again, you just break those two apart into two new tables. And I think why our database book kind of skipped the details of second and third is if you go with the definition that every determinant is a candidate key, you just sort of skip a lot of this wordiness and it naturally meets both. You kind of jump straight to the end. So here's an example with the transitive dependency. So we have sales. So A has a transitive dependency. Let's see, where is that coming here? Customer ID, customer name, salesperson. So the salesperson, the customer ID determines the salesperson, and the salesperson determines the region. So it's kind of this determines this, which in turn determines that, right? So we split those apart. So customer ID determines salesperson. Break that part of the transitive dependency out. Salesperson determines region. Break that part out. Now, that saves us kind of a minute amount of storage here because now we don't have south stored twice. You still have to store Smith because they're using Smith as the key. But this is a better design. And again, if someone changed regions, it'd be easier with the second design. Like have our own mini private class.
That's,
Yeah. Well, I mean, when you only have 6 in-person people, 10 total, you know. You're online, but you come. Damon's in person, and he usually doesn't come. So, all right, foreign keys. So that we had a foreign key right here, right? This is a foreign key to this. No, this is a foreign key to this. I said it backwards. They're underlined here. That's how they're indicating. So Smith is only once in here. This is a primary key. In here, it's a foreign key. We have more than one. So just interesting to look at their definition. Attribute that appears as a non-primary key attribute in one relation, and as a primary key attribute in another. So that's the idea. Here, it's not a key. It's not a primary key. Here it is. They're connected. So the whole point of this is referential integrity. So it specifies that the value of an attribute in one relation depends on the value of the same attribute in another. So Smith is Smith in both. And if Smith gets remarried and becomes Johnson, you just go here and change it, and this is all fixed and everything's happy. If you have Cascade, but Cascade update, right, through the key. Okay. So, kind of this process of transforming ER diagrams into relations. So, I mean, we kind of know this. You want to take that ER diagram and translate it. You don't want to just sit down and start over. You made the conceptual model for a reason. So the steps we're going to go through, and these are really similar to last semester, represent the entities. So every rectangle in your ER diagram is going to become a relation or a table in our logical model. Represent the relationships. So you look at your ER diagram and you say, do I have one-to-one, one-to-many, or many-to-many relationships? And then we did have steps to go through for that part. If it's one-to-one, you just do a foreign key, right? And you can kind of pick either way. It doesn't matter, but usually one way makes sense. If it's one-to-many, then no, one-to-many, you don't need another table. You still just put a foreign key, but there the direction matters. The foreign key is contained in the table where there's going to be more than one instance of it, like that last example. If it's many-to-many, then you have to make that extra table. So you map all that out, then you have your logical design. Then you normalize the relations. But like I've said, if you did your ER diagram well and you followed the rules, not a lot of normalization is ever really needed. I've not ever designed a database where I got to this step and I had to like really blow things up. It definitely can happen though, because in your ER there's no concept of functional dependencies. If you build a really good entity, it may have some of those functional dependencies and transitive dependencies. That's where this normalization is going to come. It's just usually, I guess I haven't, usually I've modeled things that are more, they're a little simpler, like people and that information. If you were trying to model like mushrooms, something where there's a ton of properties, you have a lot more chance of those functional dependencies within a relation and then that need to normalize. I don't really think anyone in database had almost any change from their ER other than creating the tables on the many-to-many relationships. There was not really any normalization needed. You guys didn't have any, I don't think. I'm not sure anybody did. So, and then merge the relations. So we'll see. There's a slide about merging. So I'm going to go kind of quick because this is, I mean, we've really gone over this. So each entity becomes a relation. The identifier is what we call it in the ER diagram. That just becomes the key. And there's nothing complicated. But you got to double check that your primary key meets these rules. So that value of the key must uniquely identify every row, and then the key should be non-redundant. That's if you put any thought into your ER diagram, your identifiers, you should have picked some. You should have picked first name as an identifier. Now, where this comes into play is if someone else does the ER diagram. I mean, I'm used to working in environments where I kind of do everything. So I kind of know what fed down to me was good. But if you work somewhere where they say, here's the ER diagram that we built from someone else's data flow diagram, it was built from this, because that's how it's going to work in a big company. You know, if you're just taking an ER diagram to build a database, you're going to have to put a lot more thought into some of these things than if you did it from the top down. So double check, is it really unique? Is it ever duplicated? Oh, if it's duplicated, you know, it doesn't work. So here's just a really simple example. We made a customer relation. Our customer ID dropped down, and we have all the pieces. Now, where normalization comes into play is the city, state, zip. But what I've been saying is, if you're smart about ER diagramming, would you have ever put this weird city, state, zip? So no, this was a poor ER, an entity, poorly designed entity. If you map that straight in, you're going to have to do some normalization to clean this up. It just never should have been done that way. So that's, not to rehash it. If you did them both, you wouldn't have that. So that's the joy of working with other people. Things other than that's reality. But I'm kind of a control freak, so it was nice to work in my own company where I did the database, I did the code, I did the front end design. Like, only had myself to blame. Yeah, right. So relationships, this is that second part. So one to N relationships, and they're kind of combining the one-to-one. Is there ever a one? No, there it is. Okay, they just went out. One to N. Add the primary key attribute or attributes of the entity on the one side to the entity on the N side as a foreign key. So the side that's mini, because there's going to be duplicates, that's where the foreign key exists. So in that other table, it was the left table, if we were looking at, I forget what the names of the salesperson. The mini side was on the left table where the customer and the salesperson were together. The one side migrates to the mini side. That's just what they're making. So here's our ER. And again, we're looking at the outer, the ones closest to the entity. This is a one to many relation. So we're looking at the maximum cardinality when we look at whether something is just one to many or many to one. One customer can have many orders. So the foreign key gets placed in the order. That's basically it. We took order down here and we added the customer ID. So one to many are pretty simple. One to one are even more simple, but add the primary key as the foreign key of B. Add the primary key of B as the foreign key of A. So you can go either way. Both, I don't know why you do both. I can't think of a good reason, but the book suggests that that's a possibility, but I don't necessarily see a big advantage to that. So M to N, many to many, create another relation and include primary keys of all relations as primary key in the new relation. So you make what I call the mapping table, but it's really the associative entity. Right? That's what our book, well, this book called it that too. And that's a common term. I just don't like it. But you take and make that associative entity, and you put the keys from both sides. So now here they're actually showing a three-part relationship, right? So a product has an order, and then there's an ordered quantity. So we have order line, product. Has the order number, it has the product ID, and it has the quantity. So it's not a three-way relationship, I thought it was. It's just the way they map this, or the way they've diagrammed this on the ER, is that this is a property of this relationship. We didn't really diagram them quite that way in our ERs. This is a different kind of type of structure here, right? This dashed line, that meant a strong entity in our, so I mean, they're using a slightly different format, but the idea is just that this is an extra attribute we want to store about this relationship, which is how many did they actually order. So this order, they ordered this N128, and they ordered 2. And it's pretty common those relationships will have extra data. On our orbital shift database, we had employees, we had positions that they could work in. It's many to many, because one employee can work in many positions, and of course, you have more than one person that works each position. The middle had employee per position, we called it. So it had the employee ID, the position ID, but then additionally it had their hourly rate. What do they get paid when they work for that position? Because in a lot of these places, bartender, people get paid different depending what they're working that particular day, because of tips and stuff. So that was an additional piece of information that was relevant only to that relationship. So 1 to N relationships. So yeah, relating it to itself. This is that whole recursive. So an employee has a supervisor. It's an employee related to an employee. We call that a recursive foreign key. Basically, a foreign key in a relation that references the primary key of the same relation. So a supervisor, this usually ends up kind of needing nulls, right? Because it's a supervisor. At some point, someone doesn't have a supervisor, right? So they wouldn't have a supervisor listed there, but everybody else would have another one of the employees. M to N, so we didn't even talk about these, but you can have a many-to-many within one relation. So if you need to relate a bunch of employees to a bunch of employees somehow, recursively, you're gonna have to split that out, obviously. So you're gonna make a new relation that's a composite key of like employee ID and employee ID. You'll have two. It's kind of you do see these unary ones. They get kind of funky to model and kind of confusing. So if there's a way around it, but I mean, you can see cases where that could be the case. If there's 2 managers, if you have 2 or more supervisors, and they each supervise 2 or more people, it's a unary end-to-end relationship, and you have to break that out. So here's an employee. They did the exact same one. So it's a one-to-many. One employee manages many. Looking at the part closest to the entity. Here's a many-to-many. So an item number, many-to-many, has bill of materials structures. So many items have many other items. items. It's confusing, but I guess it's because the items are put together to build other items. So you could have a chip, but then you could have the chip installed on something else. So there's a MIDI chips together, and then that same chip.
A food basket.
Yeah. Yeah. Right. So that's kind of where one item, that chip might appear on 5 different devices, but those devices all have a whole bunch of chips. So I think that's what they're getting at with this item deal. So you'd have to split out a relation of item number and item number. You'd have to give it a different name, of course. It would both be foreign keys to item, and then they have a quantity in here of how many are. So you'd have, like, your computer would have an item number, and then you'd have i5 processor, whatever number it was, would also have an item number. The computer, whatever that is, contains the i5, and how many does it have? We don't really do a lot of dual CPUs anymore, but now that everything's just multi-core, but kind of get the point. So here's just a little table that kind of just, it's nice to have these tables to reference, but regular entity in our ER to make a relational version, create a relation with primary key and non-key. Just make it, that's easy. A weak entity to create a relation with a composite primary key, which includes the primary key of the entity on which this weak entity depends and non-key attributes. So remember, we didn't really talk about weak entities even in the ER diagram, but that's an entity that can't exist without the existence of another entity. So, really the mapping into creating the database, you're just creating that second table, and it has its own key, and then it also has the foreign key of, it's kind of almost like a parent relation, and you have a composite primary key, which then is the entity of which it depends on, and its own entity. So what was a good example of databases? Oh yeah, you can't have a. Yeah, you can't have a service to call on an apartment without having an apartment. There was some of those kind of relations, like, right? Like one has to exist before the other makes any sense. You can't just have service calls in there and no apartments. I think that's what it was. And then the service call had an ID, and it had the ID of the apartment that it was related to, and then its primary key was those together, because it's going to have more than one service call. So that composite primary key, that two-part allows it to be unique. Yeah, that's a good example. And then it just shows all these other relations that we just talked about. So merging relations, which they call view integration in this book. So the idea is we want to remove redundant relations. So view integration, what are some of the problems? Synonyms, 2 different names are used for the same attribute. You might have in your database, just the attribute is titled something different, but it's really the same thing. This merging process, basically you want users to kind of agree on a single name, would be a good example. I don't know, it could just be like someone's pay. Hourly pay is called it here, and somewhere else it's called pay rate. Things like that. It has the same meaning. We're just calling it something different. We want to get an agreement on that standard name. Homonyms. So that's even worse, is when you have one name that's used for things that are completely different. So you've got to create a new name. maybe pay rate is used for hourly rate and salary rate. They're not the same thing, but the same name is being used for both. Dependencies between non-keys. So dependencies may be created as a result of view integration. So again, you just need to normalize. This whole idea of view integration is not something we really talk about in databases. I want to linger on it. It's I mean, the idea is we've done everything, we've normalized it, it meets those rules, and we're looking at it just to see, does everything in here kind of make sense? Because if you strictly follow those normalization rules and there's synonyms, it'll pass all the tests. But this is kind of a common sense look at it to say, well, yeah, it's normalized, but you've got some weirdness. So now just going into the physical file part of it. So this is kind of some new information. It's somewhat interesting, just to kind of be aware. So, I mean, this is beyond the DBMS. In order to kind of think about how we would actually store these if we weren't using just a SQL server, we would need our normalized relations and volume estimates. How much is it going to store each relation? And you can kind of estimate that. Remember, we create data types, right? Integer, bar chars. You can actually break that down into how many bytes those take to store, and then estimate how many, here's the whole set of attributes. To store one row takes this much space. How many rows do we think we're going to store? What's the storage requirement? I mean, you're not often going to have to deal with it at that level, but the definitions of each attribute, so that's kind of like the specifics, which helps with the volume estimates. Where and when data are used, entered, retrieved, deleted, and updated. So kind of knowing like certain pieces of data are going to be modified and used way more. Someone's first name and last name almost always goes in and never changes. It's very rare. It'll happen. You need to be able to change it, but it's not like you're changing it every day. Other things change hundreds of times. So there's some different constraints based on that. Expectations for response time. Do you need it fast? In today's day and age, I think we can get everything pretty fast. In the past, these were bigger issues. Data integrity. So we talked about this in database. Some of our NoSQLs, the integrity wasn't there, but the speed is. You're more concerned about how fast you can get it versus how accurate it is. So we kind of there's always trade-offs with these things. And if you were thinking about how am I going to store these in a file to get at, those are important. Technologies for implementing the files. I mean, that's kind of obvious. We're sort of glossing over that. So, field, smallest unit of a named application data recognized by system software. So this is like, I put way too much on here, but just put it out. The idea is that if we have an attribute, it's a field. It's got to be stored somewhere as a piece of data. So data types, this is what I was touching at. Internally, that's stored somehow. An integer has some internal structure, a bar chart, a date, all the things we talked about. So data type is what's the coding scheme that's going to use to store it. And it does have implications because when we retrieve that data from our database, it comes back with that type. It can be converted and stuff, but if you pick the wrong data type, it can make it a lot more painful on your programmers. We encountered that with which field was it in yours? You had to change them. It was the dates.
Yeah, I took dates out.
Because you didn't have the right PHP thing to be able to correctly convert dates. So you changed he changed all of his database to I think you just did it to bar charts, right? So it was just text. So that can have some kind of implications there. But basically what we want to do is we want to make things store and take the least space. We want to be able to have all the values that are in there. We want, obviously, data integrity, and we want to be able to manipulate that. So if I'm going to store a date, I want it to take the least space. I want to be able to represent all possible dates. I don't want it to be limited to Y2K. And that was a major flaw in designing a field, is that they didn't store the year, the first part of the year, just the trailing 2 digits. The world didn't melt down, but improved data integrity is pretty obvious. And then you want to be able to edit that date. Can I increment it? Can I make it go up by a day? Can I modify it easily? Calculated fields. So the idea is we don't want calculated fields, right? If I list someone's birth date, I don't need to store their age because I can easily calculate that. Today and subtract their date, age from it, and I'll get how old they are. So data integrity. Now these, like I said, they're kind of looking at it from the physical file structure. In terms of what we're used to doing, we're just dealing within our DBMS and choosing what data type it is. Kind of helps us hit a lot of these. If you were going to store it manually and write it to a file, you'd have some other issues to think about. So default values. So remember we have these. This helps with data integrity. If something's not entered, it's good to give it a default. Input mask. So an input mask is like on a web page, when you go to enter a date, does it automatically put slashes, or does it put hyphens? Social security numbers, phone numbers, input masks can help. And the idea there is that the input mask forces it to be. Oh, I missed the last. I didn't finish taking that. It restricts the input to be what you want. If I want a phone number, I want to be sure they enter the phone number correctly every time. If I start just storing random text of what they enter, I'm going to have some that are 1406. I'm going to have some that are 406. I'm going to have some that don't even have the area code. And all of a sudden, it's the idea of good in, good out. If I don't have good data coming in, never going to get good data coming in. Referential integrity, we're not going to make it all the way through. So let's find out. So basically, we can apply extra constraints, saying by doing our foreign keys, right? Things have to exist. One thing has to exist for another to exist. So this is just kind of a rehash of this fits under the umbrella of data integrity. Null values. So not the same as 0 or blank. It basically just means it's missing. But remember in database, we talked about 3 problems. You don't know what it means. So is it missing? Did they just not enter it? Is it unknown? Like the social security number for a foreign person. That just doesn't exist, right? But if I saw that entry in there, would I know, well, did they just forget to enter it? Is that person foreign? That just you just don't know the specifics. Sometimes you have no choice. Now, you'll see people do things like, say for that, maybe they put a code in that's like F. I mean, that can be okay, but it can also cause a lot of weirdness. Like F would be foreign. So here's some referential integrity. I mean, I think we're pretty comfortable. Customer order has a customer ID. If I try to edit this to be something that doesn't exist here, the database stops me. It doesn't let it happen. Same here. I can't set the supervisor of an employee to be some ID that doesn't exist. But this case needs to be null, and also for this, this one's not null, but this one needs to be null because a supervisor doesn't have a supervisor. Well, ultimately, you get to the owner, I guess, and they technically, well, the board of directors, right? So, I mean, it just depends on what you're looking at, but what level you're modeling. So we'll stop there. We'll finish up. There's about 10 slides with our stuff on Thursday. Probably what'll happen is I'll finish this Thursday. I'll go into chapter 10, and then the beginning of class on Tuesday, I'll finish chapter 10 before the exam. The slides are there and the book is there to study, but I'll finish talking about chapter 10 for the first 20 minutes, and then we'll have the last hour to take the exam. Make sense? All right, so keep your eyes open for study guide and homework 3 shortly. Okay. Bye on YouTube's.